Hi guys, can you all hear me?
Hi, yeah, hi, Bhavya.
Hi Prithvi.
Yeah,
Sorry.
hello everyone. Good evening.
Yeah, hope everybody is able to hear us. Please confirm. Prithvi, can you share your screen once?
Yeah, sure.
So in the currently we are going on day 4 with respect to our Silicon Symphony VLSI masterclass, guys. And we have discussed about what is VLSI, how VLSI is different from embedded, what is the market for VLSI, how are we going to get through into the industry through VLSI, how is it beneficial if we learn it, what are the aspects of VLSI, and then we have seen some of the coding tools that are seen in VLSI. Along with that, we have also seen the different
Yeah, hope the screen is visible, right?
what we are seeing your Gmail.
Oh, okay.
Yeah, great.
Okay, okay.
Yes. So today we're going to talk about the modules in VLSI with respect to your coding. Yeah. So Prithvi, I think
Yeah, okay.
start on. Your screen is not presenting.
Not in presenting mode.
Yeah, it's in normal.
I got you. Okay, okay.
Yes, you can go on, Prithvi. Thank you.
Okay, yeah. Okay, guys. So yesterday we have seen a basic code for AND gate, right? And I hope everyone was able to understand yesterday's code on how to write our basic code using free simulators that were provided to us. That is like EDA Playground. And I have given you some tasks also, right? Like, I have asked you to write few other logic gates. Hope you all have done that and you have analyzed its equivalent waveforms. Okay. See, writing code is not important in here. What is important is you have to analyze your waveform. More you are into waveforms, more is your debug ability or your understanding ability. Okay. So now let us see, like, what is the difference between our Verilog language and our traditional languages. Okay. See, our traditional languages like C, they are used for programming like general purpose programming, okay, which can be used to build databases, operating systems, compilers, interpreters, lot other systems. For example, the classic example which every one of you might be aware of is, when you go to a bus pass renewal counter, there that guy will he used to renewal your bus pass or whatsoever, and the software that they use is a visual basic software. If you look at the soft code, you will be amazed, like, it is less than 2000 lines of code. Basically that is done by using some languages, some traditional languages. And in contrary to that, Verilog is a HDL language which is used for describing a hardware. As we have discussed, as I told you, HDL is for hardware description language. But here, the major difference between traditional languages and HDL is that traditional languages do not have notion of time. But whereas our HDLs have notion of time. What do I mean by notion of time? See, for example, I have written some code in C language, some 10 lines of code I have written. So after executing something around fifth line, before executing the next subsequent line, can I tell my compiler to wait for something around 10 nanoseconds? Can I tell my compiler to do that? Can I tell my compiler to wait for 10 nanoseconds? It is not possible. Okay, but in Verilog, it is possible. Even in fact, in our yesterday's coding session, we have seen, we have taken one initial block. In that, I have written something like this: hash phi a equal to one tick b1. I have written something like this. Means what? Here I am waiting for 5 time units. Okay, here the concept of time came into picture. Okay, so these HDLs will be having a notion of time into them. Okay, as C language is used for building operating system, databases, compilers, then what is Verilog used for? By this time we are already familiar with this, like it is used to describe the digital systems. How to distinguish between different files? If it is verilog file, it will have .v extension. If it is system verilog, it will have .sv extension. If it is C, it has .c extension. Apart from this, there is a very major difference between our traditional languages and the uh, uh, HDL language. Can anyone say that? We have discussed that multiple times in our due course of time. Can anyone see? The difference is synthesis. Okay, synthesis. All our existing languages cannot be synthesized. All our programming languages cannot be synthesized except HDLs. Okay, only the Verilog or the VHDL are the only languages which can be synthesized. So this is where it differs from our traditional programming languages. What is synthesis? Synthesis is nothing but whatever the code or the HDL code that you have written, that code will eventually be converted to its equivalent gate level netlist. Okay, we have seen yesterday we have written code for AND gate. So after synthesis, what happens? Whatever the code that you have written, it will be converted into its equivalent CMOS transistors. Okay, that is the beauty of the HDL language. Like it can be synthesized. Okay. So as I have told you yesterday, like there are two HDL languages. Okay, there are two HDLs. One is Verilog, other one is the VHDL. So what is the difference between these two, Verilog and VHDL? See, Verilog is most both of them are used to model electronic systems only, but in specific, VHDL is used for mixed signal design systems, and it is also used in automation. Okay, and mostly VHDL is used in defense applications. You know, mostly it is not that 100% it is used, but mostly VHDL is used in defense applications. In fact, when I was in my UG in my BTech, I have worked for RCI. I have worked for RCI. I have done project from RCI, where I have developed a Vedic multiplier. Okay, there I have developed something like a Vedic multiplier. There, the scientist over there who was guiding me, they insisted me to use VHDL exclusively. What I want is I want to use Verilog as it is quite easy in comparison with Verilog, VHDL. But they do not, they don't want me to use Verilog. So majority of defense applications will prefer VHDL. Okay, and VHDL is a strongly typed language, whereas Verilog is a weakly typed language. I hope you guys have some idea on what is a weakly typed language and what is a strongly typed language. If not, let me know. I will let you know. Okay, and see here, Verilog is similar to C language, whereas VHDL, it is pretty old and it is based on our Pascal or Ada languages. And Verilog is a case sensitive language, whereas VHDL is not case sensitive. What do I mean by this? It means that, for example, if I write like this, int A and int capital A, okay, Verilog will treat both of them as a single variable. But if it is VHDL, it will treat these two things as two different variables. For it, small a is one variable, capital A is another variable. So this is not case sensitive, whereas this is case sensitive. Okay. Sorry, did I tell it reversely? Okay. VHDL is not case sensitive. Okay. But Verilog is case sensitive. Means it is practically able to distinguish what is capital A, what is small a. But here, for VHDL, both of them look same. Okay, and as I told you, VHDL is older older than Verilog. So it means that obviously it has some complex data types. So all those complex data types were simplified, and VHDL is having many bottlenecks into it. So all those bottlenecks are simplified and some simpler data types came into the picture. So VHDL is quite complex, and enhanced or simplified version of it is Verilog. Okay, so this is about the differences between our two HDLs, that is Verilog and VHDL. The advanced version of Verilog is System Verilog. Okay, and we'll be discussing few thoughts on insights about System Verilog in our next day session. Okay. So as we have already seen this, like what is the importance of our HDL languages? See, for example, in your under UG, okay, or in you might be having some lab like EDC or Analog Electronics Laboratory, where they will give you some BJT. I don't know whether BJT is still alive or not, or you know. So they will give you a BJT and they will ask you to what do some experiment on this in such a way that you have to determine its region of operation. You have to determine something like this. So what you used to do, you generally used to take a breadboard which has some series and parallel connections, right? And you used to connect it with some resistors, and you used to have some CRO, some oscilloscope. You used to connect with the voltage supply, something, and you used to verify it, right? So for a single uh, BJT, how much amount of space you have consumed in order to verify it? Yeah, it's huge space, right? Probably I could say it is 10 by 10 centimeters. For example, what if I ask you to verify op amp? Operational amplifier. Operational amplifier is something like this. It looks something like this. Okay, which has a inverting and non-inverting terminal. It's see the operational amplifier will be having approximately 26 transistors into it. So if I ask you to verify this operational amplifier which has 26 transistors into it, how much space will you be consuming? Probably half of your laboratory. More than half of the space of the laboratory will be consuming just to verify single op amp. For example, if I give you a chip which has some, assume that it has 10,000 transistors into it, and if I ask you to verify it, how will you verify it? Your campus alone is not enough. You have to borrow your neighboring campus, your college campus, and arrange everything in some series or parallel connections, and you do lot of computations. Then you might be coming to conclusion. So our whatever we have done, that was what traditional schematic based design, and that is pretty difficult, highly difficult. Not difficult, it is impossible, because nowadays microprocessors are coming with trillions of transistors into them. If you see, Nvidia has recently released an AML machine, AML chip, which has trillions of transistors into it. Can you verify that manually? Not possible. So traditional schematic based design is quite difficult. That is biggest advantage of these HDLs, where everything can be simulated online. Okay. And see, as I have told you, like we need not to bother about fabrication technology. Like, whatever the thing that you have used at 1000 nanometers, you can use that at 3 nanometers, even at 5 nanometers. And by using this HDL, functional verification is quite easy. Okay. Okay. Now let us see like what are the different levels of abstractions in Verilog. Basically, you see, as we have seen yesterday, this is how basic code of Verilog looks like. It will be having a module and end module, followed by some module name and some terminal list, or I would say port list. Then you will be writing some core logic in between the module and end module. Okay, that is how generally the structure of a Verilog code look like. And in between this, like there are many things that you can do. Like how you can write the code within this module and end module. So you can write it in many ways. Like there are different levels of abstractions in Verilog. Okay, different levels of abstractions in Verilog. Like behavioral modeling, data flow modeling, gate level of structural modeling, switch level modeling, and mixed modeling. So there are different levels of abstractions. Among all these things, behavioral modeling is the highest level of abstraction. Okay, this is the highest level of abstraction. So the question comes is, what is this abstraction here? Hmm? What is the generalist English meaning of abstraction? Abstract, see, you might have published some research papers, or you might have written some thesis document in your final year, or if at all you were doing some project in between, the first page of your thesis would be having something like an abstract. So what does that page of abstract tells? It will tell you like your project is about what. So if someone wants to know what your project is all about, they need not to go through the entire document. It is enough for them just to read the abstract, so that they will be able to know it. Means, what does this abstract tell you? Abstract will give you a greater level of understanding over the thing within a short span of time. Okay, what is abstraction? Abstraction is nothing but, in my way, I would call abstraction is nothing but level of understanding. Okay, how easy is it to understand is what being told by abstraction. And here I am telling you There are many levels of abstractions like behavioral, data flow, gate level or structural, switch level, and mixed modeling. So, and what am I calling? Among all these levels of abstraction, I am telling that behavioral is the highest level of abstraction. Why? What is the reason behind? And switch level is the lowest level of abstraction. Switch level is the quite lowest. Why? What is the reason behind I'm calling these things? So I will tell you. We will come to that point now. Okay. So see here, switch level is nothing but everything you will be representing in terms of its equivalent switches. Whatever the thing that you write in your code, that thing will be represented in terms of its equivalent switches. You all know, right? A CMOS transistor, it looks something like this. So can this guy act as a switch? Yes, a CMOS transistor will absolutely act as a switch. So here what we will be doing in switch level modeling style is we will be representing everything into its equivalent switches. For example, let us take an AND gate. So if you take an AND gate would require how many MOS transistors? Can anyone tell? Y equal to A and B. Can anyone tell how many MOS transistors does the AND gate require? Yes? Can I see that through comments? Yeah, it requires typically 6 transistors. Okay, it requires 6 transistors. See, Y equal to A multiplied with P. It means that it requires 2 PMOS transistors and it requires 2 NMOS transistors. So these NMOS transistors should be connected like this in series and 2 PMOS transistors should be connected in parallel like this, right? So this will give you what? This will give you AB bar. And again, what you need to do? You need to convert a MOS transistor pair to this. So here what you will be getting? AB. So see here, in switch level, if at all you want to implement the functionality of a single AND gate, how many transistors you have to take care of? 6 transistors. 1, 2, 3, 4, 5, 6. For a single AND gate, you have to take care of 6 transistors, guys. Not just that, for each transistor, you have to control 3 parameters like gate to source voltage, gate to drain voltage, and gate voltage. Means totally you have 6 transistors. Each transistor is having 3 parameters. Means totally how many parameters you have to control? 18 parameters you have to control. These 18 parameters for what? In order to achieve functionality of a single AND gate. For example, if I want to simulate the behavior of an XOR gate, can anyone tell me like how many MOS transistors are required for an XOR gate? Equation looks something like this, no? A bar B plus A B bar. Can anyone tell like how many MOS transistors are required for this? How many MOS transistors? Okay. I don't know whether you guys are responding or not, but okay, let me explain it to you. See here. See, for A bar, it means that I need one inverter. It means 2 MOS transistors. Similarly, for B bar, I need 2 more transistors. And in order to implement multiplication, that is AND gate functionality, I need 6. Here also one more AND gate functionality. I need 6 more. And what else? What else? See here. Here I have OR gate operation. Even for OR gate, I need 6 more MOS transistors. Means totally how many I need? I need 22. 6 plus 6 plus 6 plus 2 plus 2. It means that I need 22 MOS transistors. And each transistor has to control, for each transistor I have to control 3 parameters. It means that just to have the functionality of a single XOR gate, I have to control how many parameters, guys? 66 parameters. You see, that is highly not practical. That is the reason we say switch level is the lowest level of abstraction. Okay, in fact, you will only justify at the end of the discussion like what makes behavioral highest and switch level lowest. Okay, so now let us, so for example, see here, if I want to achieve the functionality of the same thing in data flow, how can I write the code? If it is switch level, we have seen for an XOR gate, how many transistors required? 22 transistors. It literally means that you have to write at least 22 lines of code. If it is switch level, I have to write 22 lines of code. If it is data flow, I will simply write like this. Whatever we have seen yesterday is a data flow style of modeling. I will be writing like this. Y assign y equal to a bar b plus a b bar. That's it. In single line, I am done with coding. Now, you tell me, you compare these two things, this data flow style of modeling and switch level modeling. You compare these two. Among these two, which one is easy for you to write code? Or which one is easy for you to analyze? Data flow or switch level? Among these two, which one is easy? As per you, you tell me. It is obviously data flow, right? Obviously data flow, because in single line I am writing my code, I am done. But if I want to go to switch level, I have to take care of, I have to write 22 lines of code, not just that, and 66 parameters I have to control. Why should I do that? So now tell me, among data flow and switch level, among these two, which one is highest level of abstraction, guys? Means which one is easy for you to understand, more easy for you to understand? It is data flow, right? So among switch level modeling and data flow modeling, which one is at highest level of abstraction? Which one is at highest level of abstraction? It is obviously data flow, because data flow is easier than switch level. So that is the reason I'll call my data flow as highest level of abstraction in comparison with switch level. Okay. Now let us see the gate level. Let us see gate level. In gate level, what we do is, see, for example, let us take an example of a 2 cross 1 mux. Okay. So how does 2 cross 1 mux look like? Something like this, which has S as selection line, A, B as input, Y is the output, right? And its characteristic equation is Y equal to S bar A plus S B. Now, if I write its equivalent gate level diagram, how many gates does it require? Tell me. AND gate, OR gate, NAND gate, like that. See, in order to implement the functionality of S bar, I need a NOT gate. So if I give S here, I'll get an S bar here. And then I will collect it to one AND gate. So this is my A. So what do I get here? S bar A. And see here, I'll connect this S to one more AND gate and B here. So what do I get here? I'll get SB here. Now I need to connect these two things to a OR gate. So that what will I get here? I'll get S bar A plus SB. Correct? Yes or no? See, it means that for a given characteristic equation of a 2 cross 1 mux, this is its equivalent gate level representation. Correct? Now, if I want to write code for this in gate level, writing code in gate level is nothing but here you have to describe each and every gate here. Okay, here in gate level, what you have to do? You have to describe each and every gate. How many gates are here as per you? See, this is 1, 2, 3, 4. Totally, how many gates are there? There are 4 gates. It means that how many lines of code you have to write here? At least 4 lines of code you have to write. Okay, at least 4 lines of code you have to write, because in gate level modeling, what we will do is we will represent each and every gate. Okay, we will represent each and every gate. That is the reason it is known as what? It is known as gate level or structural modeling. Now you compare with the data flow. So here the code for gate level typically looks something like this. We will discuss one sample code on gate level also, but for now you just go with this. Initially I need a NOT gate, right? So I'll take something like this, NOT of S bar comma S, and then I will write something like this, and of some, X comma S bar comma A. I know you don't know how to write this, but we will discuss it later. But for time being, you just go with this, Y comma S comma B, and then R comma uh, something like Z comma X comma. So we write something like this. Don't worry, I'll explain you this later. So here, how many lines of code I have to write? 1, 2, 3, 4. But if it is data flow, how many lines of code I will be writing? Assign Y equal to S bar A plus SB. Done. Now you tell me, among data flow and gate level, which one is easy for you to write code? Come on, which one is easy for you to write code? It is obviously data flow, right? So now you tell me, among data flow and gate level modeling, which one is at highest level of abstraction? Which one is more easy for you to write? It is obviously data flow. In comparison with these two things, it is obviously data flow. So now if I ask you, like in comparison with gate level and switch level, in comparison with gate level and switch level, which one is easy for you to write code? If it is switch level, if at all you want to achieve this functionality, you need n number of gates, many, for AND gate you need 6. Here 6 more, 6 more, and here 2 more. So totally you need 20 gates. If it is switch level modeling style, you need 20 gates and each gate has 3 parameters to be controlled. It means you have to take care of 60 parameters. But if it is gate level, it is 4 lines of code. Now you compare switch level and gate level. Among these two, which one is at highest level of abstraction? As per you, obviously gate level. Now you compare gate level and data flow. You compare these two things now, gate level and data flow. Among these two, which one is highest level of abstraction? In gate level, I have to write 4 lines of code, but if it is data flow, single line of code is enough. See, what we are seeing here is a 2 cross 1 mux, but what if I have something like a 16 cross 1 mux? How lengthy its equivalent gate level diagram could be? And how many gates would be there? Many number of gates. So how many lines of code you will be writing for its equivalent gate level? Maybe something around 100 lines. But if it is data flow, single line is enough, bro. Okay, just single line. So as of now, if we keep behavioral aside, okay, can you guys tell me, like, what is the order from highest to lowest with respect to its abstraction levels? Data flow will be the highest level of abstraction as of now. After this, after data flow, it is gate level, and after gate level it is switch level being the lowest, and we know the reason why switch level is lowest, and we know the reason why gate level is slightly more than switch level and less than data flow. What about behavioral? See, in behavioral modeling style, what happens is, okay, even before going to behavioral, in data flow, see, what we are writing is something like this: assign y equal to s bar a plus sp. We are writing something like this. What is this? What is this? This is a characteristic equation. But if it is behavioral modeling, we will be writing something like this. If s equal to 0, y equal to a, else y equal to b. We write something like this. And I mean, this is a core logic. In between, there are a lot other things. So by looking at this, like, if s equals to 0, y equal to a, else y equals to b, there are 4 lines of code. But here, there is only single line of code in data flow. But still, I am calling behavioral modeling as the highest level of modeling. Why? Yeah, that's the basic question, right? So the actual reason is, see, here you might be feeling data flow as easy because you already know the characteristic equation here. For example, if I ask you to write code for 64 cross 1 mux using data flow, 64 cross 1 mux means you have to solve 5 variable k-map, not 5, 6 variable k-map. Yes, in order to come to conclusion, or in order to form characteristic equation, how many variable k-map you have to solve? 6 variable k-map you have to solve. People will struggle to solve 4 variable k-map, and you might have hardly solved 5 variable k-map. But if it is 6 variable k-map, you will die. It is, next to impossible, right? So data flow is easy unless you know the characteristic equation, but it is not that you always know the characteristic equation in the real-time design. Okay, in real-time design it is highly impossible. So all your practical or real-time designs for coding will be done in behavioral modeling only. It will be done in behavioral modeling only. And same thing, if it is 64 cross 1 mux, right? So it is, you have to solve 6 variable k-map, but there is no such thing required in behavioral modeling. Okay, you can write this code very easily just by using if else statements, or in behavioral modeling you can even write it in single line. Okay, even though it is 64 cross 1 marks, 128 cross 1 marks, or 256 cross 1 marks, whatever is the size of the marks, it doesn't matter. You can write the code using behavioral style in single line. Now you tell me, based upon the discussion we had so far, among behavioral and data flow, which one is easy for you to code? I know I did not give proper insight into this because as you will be able to come to proper conclusion if we had a full-fledged course or full-fledged discussion. But as of now, based on what we have discussed so far, among behavioral and data flow, can't I call that behavioral is the highest level of abstraction? Obviously, I can call. So now you guys have to answer me. Like you tell me, what is the different levels of abstractions in Verilog? Come on, levels of abstractions. I'll be seeing your chat box now. I want you to, write them in a sequence from bottom to top. Means from lowest to highest. I want lowest level of abstraction to the highest level of abstraction. Can you guys reply with me? Reply to me for that. I said bottom level of abstraction to the top level abstraction. I want lowest level of abstraction first. Okay, okay. Yeah, that's good. Great, great. Thanks for the response, guys. So see here. Among all these modeling styles, okay, among all these modeling styles, which one is the lowest level of abstraction? We have seen switch level. Switch level is the lowest level of abstraction. And second lowest is gate level. Okay. And highest is behavioral. Second highest is data flow. So if I ask you to write them in proper way, uh, in levels of abstraction, that is from top to bottom, then highest level of abstraction is what? Behavioral modeling style. And second highest is what? Data flow style. And then the gate level. And the least is the switch level modeling style. Okay, so there are in Verilog, broadly there are four modeling styles: behavioral, data flow, gate level, and switch level. And among all these things, lowest is the switch level. Why switch level is lowest? Because it is difficult. It is quite difficult just to implement the functionality of a full adder, okay, which has one XOR gate and one AND gate and some OR gate. So even in order to execute this, you have to write approximately more than 60 lines of code you have to write. That is quite difficult. That is the reason switch level is the lowest, or it is quite difficult. Then gate level, then data flow, then behavioral being the highest level of abstraction. Okay. So this is about different levels of abstractions in Verilog. Now, okay, we have discussed this already, right? Different levels of abstractions like behavioral, data flow, gate level, and switch level. Okay, so okay, now let us quickly try to write one code in gate level modeling. Okay, so let me write one code in gate level modeling style. Okay, yeah. So see here, what is the first thing we have to start with? Module, right? And the name of the module is something like gate level. Okay, and oh, here, so for what shall we write the code? Shall we write the code for 2 cross 1 marks, guys? Okay, 2 cross 1 marks requires how many inputs, how many outputs? Can you guys help me with that? Yes, tell me how many inputs, how many outputs does it require? It requires three inputs: A, B, selection line, and one output. So I have to take here totally how many ports required? 4. A comma B comma S comma Y. I need 4 ports, and then if there is a module, there should be what? End module. And now what I have to do here? I have to give them the direction. Input, among them, what are the inputs? Here A comma B comma my selection line S are the inputs. What is the output here? Y is the output. Simple, right? And we want to write the code in what style of modeling? Gate level. So let us try to write its equivalent gate level diagram here. Try to write the equivalent gate level diagram. So this is S, and what is this? This is S bar. This is A. So what do I get here? I'll get S bar A, and then what do I get here? SB. Now I'll connect these two things to a OR gate. So what will I get here? S bar A plus SB. So here one thing you have to observe here is uh, just a minute. Okay, so see here, what I'll be doing here is see, this is my input port, right? And this is also my input port. Here, this is also my input port, and this is also my input port, and this is my output port. But what about the remaining things? What about these remaining things? See, what is this? What about this here? What about this? And what about this? What are these things? They are neither inputs nor outputs, no? So what are they? Actually, they are some intermediate connections. Okay, what are they? They are some intermediate connections. So I will call them as wires. So I will call this as wire 1, and I will call this as wire 2 W2, and I will call this as what? Wire 3, that is W3. So in order to achieve the functionality of a 2 cross 1 mux using gate level diagram, using gate level modeling style, how many intermediate connections do I need here, guys? See, how many intermediate connections am I having? See, W1, W2, W3. So totally, how many intermediate connections do I have? 3 intermediate connections. Here, intermediate connections are nothing but wires. So apart from inputs and outputs, what else should I declare here? What else should I declare? I have to declare wires. How many wires do I need? I need 3 wires like W1, W2, W3. You can have your own name to your wire. And then, now what I have to do? I have to write code. So see here, not of, currently I'm writing code for not gate, not of W1 comma S. That's it. It means what? It means that W1 will be equal to S bar. Okay. Here, okay, let me tell you this thing. If I write something like this, and of A1 comma A2 comma A3, it means that A1 is my output and A2 and A3 are my inputs. It means that A1 equal to A2 ANDed with A3. That is the meaning of it. Similarly, if I write R of x1 comma x2 comma x3, it means that x1 is equals to x2 plus x3, or x2 ORed with x3. That is the meaning. Similarly, what did I write here? Not of W1 comma S. So what does it mean? It means that W1 is equals to S bar. Okay. So far so good, right? That is the meaning of it. So here, what did I write here? Not W1 comma S. Now I have to write code for what? Let us write code for this AND gate now. Let us write code for this particular, this is the first one. And let us write code for the second one now. How can I? Then we will be writing for third one. Now let us write for second one. In second one, what do I have? And of, okay. Here, what is the output of this second gate? See, W1 is the input that we can see here, right? W1 is the input. Another input is what? Another input is A. What is the output? Here the output I have taken is W2. So here I will be writing it something like this. I'll be writing it something like this. See here, W2 comma, come on, can you guys help me with this from chat box? Output is W2. What are the inputs? W1 is one input. And what is the other input? A is the other input. Okay, so here what is happening? W2 is equals to W1 ANDed with what? Oh, it should be comment, right? W2 equals to W1 ANDed with A. This is it. Indeed, here, what is W1? W2 equals to, what is W1 here? S bar. That is S bar A. Correct? Now, let us go with the second AND gate. AND of, what is its output? What is the output of the third gate? W3 is the output, right? And what are the inputs? B is one input, S is the other input. So let us write the same here. Okay, so W3 is my output, and then S comma A are my, sorry, it should be B, right? B are my inputs. So what does W3 look like? W3 equals to S ANDed with B. As simple as that. Next what I have to do? I have to write code for this fourth gate, that is OR gate. So how can I write it? OR of, come on, what is the output? See, our Y is the output. Okay, Y is our output. So Y comma, what are the inputs for it? What are the two inputs? This is one input. This is the other input. This input is what? W2 and W3. So R of Y comma W2 comma W3. Same thing we'll be writing here. See, R of, what is the output? Y comma W2 comma W3. Okay, that's it. We are done with the coding. Once look at the code, it is crystal clear here. How many gates do I have here? 4 gates, right? And how many lines of core logic I have written here? See, line number 6, 7, 8, 9. Not gate, 2 AND gates, 1 OR gate. So I have represented the functionality of 2 cross 1 mux in a gate level fashion. Done. We are done with the coding of our DUT. So basically this is how you have to write code for a given functionality in its equivalent gate level diagram. So what is important here is declaring the intermediate connections. So how many intermediate connections did I take here? 3 intermediate connections. They are wire W1, wire W2, wire W3. So intermediate connections in Verilog are declared with the keyword something known as wire. Okay, something known as wire. I have declared them here in line number 5. Okay, so now what we have to do? We have written the code. Fine. Our DUT is ready. Okay, our design is ready. Now what we have to write? The test bench. Now we have to write what? Test bench. So let us quickly write test bench for this module, like ABC. Okay, if there is a module, there should be end module, and inputs must be declared as what? Reg A comma B comma S, and then outputs must be declared as wires, wire Y, and we need not to take care of these things here. Okay, here in my DUT or in my design, I have declared some wires, right? You need not to tackle these things or take care of these things in your test bench. Okay, you need not to bother about that in your test bench. Now wire Y is done. Now what I have to do? As per your yesterday's knowledge, what I have to do now? What is the next step I have to do? I have to do something known as what? Module instantiation. So here I will be taking something like A1 as the instance name. Okay, what is this line number 6 talking here? Telling us it is instantiation. This is module instantiation. Then I have to take one initial. I have to take one initial begin end block. In between this, what I have to do? I have to write my core logic. Like, selection is 0, And like what are the inputs I have? A comma B, right? A equals to 0, B equals to 0, something like this. And then I will give some delay of 5 time units, and then I'll give like S equals to 0 and A equals to uh, okay, some random values we can give. 0, B equals to 1, something like this. Okay, sorry. Oh, okay. Okay, I have given some I'm trying to give some logic here. Okay, so 0 0, now I'll give it as 1. Okay, I'll give it as 1, and again I'll give some you can give any value. Okay, make sure that you're covering all the range. 0 0, and here I'll be giving something like 1 0. Okay, here again some 1 1 we will give. Okay, make it 1, and here I'll give 1 1, and here I'll give something like 1 0. So it is up to you, you can give any random value. Okay, but what we have to make sure is we are covering all the possible values. So I have given some stimulus here, or I have given some input test vector. Okay, done. What else we have to do now? Let me erase this part from here. Yeah, now what else I have to do, guys? Hmm? Here I have to go and select the tools or simulators, and from here I have to select any one simulator. For today, let us select Cadence Helium and save the code. After saving, I'll click on open EP wave after run. I'll click on open EP wave after run. There is one option here, right? Then save again, run again. Now you will see one error. Okay, you will see one error now. So copy this error, and what you have to do, take one more initial block, just paste it here, and like so you give some delay. Okay, something like 100, and finish it and end this. That's it. Save it and run it. So we will be able to see some waveform. Okay, if at all you are not able to see waveform, what you have to do is go to get signals, select this, and there is an option like append all. So you will be able to see those signals. Okay, now see here, can you guys observe the function, whether the functionality of 2 cross 1 max is happening properly or not? Okay, let me help you here with help of its truth table. Like y, okay, select S is the selection line, A and B are the inputs, Y is the output, right? So tell me what are the outputs? See, if selection is 0, oh okay, this is B, okay, this is B, this is A. Here this guy is B, this guy is A. If selection is 0, what is the output you will be seeing? It will be A, right? Output will be A, that is 0. If selection is 0, 1. If it is 0, output will be A. Selection is 0, output will be A. If selection is 1, okay, just a minute. Let me write the whole thing little bit in a spacious way. Okay, sorry for that. Okay, this is my B, this is my A, this is my selection line, this is my output Y. Okay, now see. Still space is not sufficient. Okay, so see here, if my selection is 0, what is the output? Output will be the variable a. What is there in a? 0 is there, so I will be getting 0. If my selection is 1, I will be getting b. What is there in b? 0. Again, if my selection is 0, what will I get? A, that is 1. If my selection is 1, b, I'll get as an output. Similarly, if selection is 0, I'll get a. If selection is 1, I'll get b. So the functionality is something like this. Now let us see whether we are getting the same functionality in the waveform or not. So for instance, let me place the cursor at 0 nanoseconds. Now see here, my current time is 0 nanoseconds. And what is the value of a? Value of a is 0, b, b is also 0, and selection line is also 0. If selection is 0, which value will it select? A or b? It will select a. And what is the value that is there in a? 0. Is the same value coming to your output or not? Are you able to see the same value of a onto your output or not? Yes, you are able to see. Okay. Now let us go to the next observation point. Okay, let me place my cursor somewhere around here, because here, okay, let me place it here. So now see here, what is the value of a? Here a is 0. What about b? What about b? B is also 0. What about selection line? Selection line is moving from 0 to 1. So if selection line is 1, which value will it pick? A or b? It has to pick b. What is there in b? I have 0 in b. So is the 0 captured to output or not? Yes, I'm able to see the value of 0 into my selection line. Or even from this you can say AB are 0, 0, selection line is 1. If selection is 1, which has to propagate to the output? Whatever the value that is there in B. So 0 is there in B, same thing is coming. Okay, fine. Now let us go to the next thing. Next observation point, like this. Okay, I am going to this point now. Here, what is the value of A? A is 0. What is the value of B? B is 1. A is 0 and B is changing from 0 to 1. B is 1. And what is the value of selection line? Selection line is 1. If selection line is 1, which value will it pick? A or B? It will pick B. What is there in B? 1. So, is the same thing captured to the output or not? Yes. See here. That is what we can see. The Y is being transmitted, going from 0 to 1. Why it is going to 1? Because 1 is there in B. See, in B I have 1 and the same 1 is captured to my output. That's it. Now, like this, we have to analyze. For example, let me place my cursor here. Okay, let me place my cursor here. Okay, at 25 nanoseconds. So, at 25 nanoseconds, what is the value of A? A is moving from 1 to 0. And what is the value of B? B is still 1. And what is the value of selection line? Selection line is 0 here. So if selection is 0, see here. If selection is 0, which value should my output pick? It should pick the value that is there in A. In A, what is there? 0. Is the 0 propagated to output or not? Yes. So see here, 0 is there and same 0 is propagated to the output. That's what we can see here. My output is changing from 1 to 0. Okay. This is how you have to verify your waveform. Whether it is 2 cross 1 marks, 4 cross 1 marks, or whatsoever is the size of the multiplexer. This is the way to verify it using waveform. Okay. Any doubts here to anyone? Now I am open to doubts. Yeah. Okay. So before coming to doubt session, so let me tell you one thing. So today, what we have seen, yesterday, what we have seen is how to write code using data flow style of modeling. In data flow, what you will be doing is you will be using a keyword known as assign, and you will be writing some code. Assign y equal to, you will write something like this, s bar a plus sb, and that's it. If it is gate level, what you will do, you will use equivalent gates and you will write the code. So we have seen among 4 levels of abstraction, we have seen how to write code using 2 different modeling styles. One is the data flow style of modeling, other one is the gate level modeling. And tomorrow we will be seeing how to write code in behavioral style of modeling. Okay, how to use behavioral style of modeling, and I will give you a few brief introduction about system verilog, UVM, and what are different protocols. Okay, what are different protocols that were available in industry, and what is the significance of a protocol, like why should we need a protocol, or like what is its practical significance in real life, real time. So these things we'll be discussing tomorrow. Okay, and we will be winding up this session with tomorrow's discussion. Okay, so please do attend tomorrow's session, because in tomorrow's session what I will be discussing is, like, this will be the core part of tomorrow's discussion, like what is a protocol and what is its significance, why should we have a protocol into our chip, what does it do, how does it communicate the things, how does it transfer the data from one device to the other, or from within one module to the other module. All these things we'll be going to discuss tomorrow. Okay, yeah, I'm done with the class for today. So if you have any doubts, please, I'm open to doubts.
Thank you, Prithvi. Can you explain the waveform again? Is a question from Nikita.
Yeah, sure. See here. Let us, I see, I am placing my cursor here. Okay. Now see. Here, what is the value of A here? Value of A is 0. What about B? What is the value of B? B is 1. Okay. A is 0. B is 1. What is the value of selection line here? Value of selection line is how much? 0. Okay, then for this instance, what should be the output y? Tell me. If selection line is 0, it has to pick the value whatever that was there in A. What is there in A? 0 is there. So my output should be 0 here. Am I seeing the same here or not? Yes, I am seeing. See, my output is 0 here. So my A is successfully propagated to output. My input is successfully propagated to output when my selection is 0. For example, let us take one more observation point. Okay, let me put my cursor somewhere around here. Now you see here. Here, what is the value of A and B? What is the value of B? What is the value of A? What is B here? B is 1. Okay. And what is A? A is 0. Okay, fine. What about selection line? What is the value of selection line here? Selection is 1. Or, okay, let me explain you this way. This is A, this is B, this is selection line, this is output. Now, here, okay, this is A, this is B. A is equal to how much here? Here, A is equals to 0. B is equal to how much? B is equal to 1. What about selection? What is the value of selection line here? Selection line is 1, right? So, for this configuration, tell me what is the value of output you will be seeing. Selection is 1. If selection is 1, output will be equal to B, right? So what is there in B? 1. So your output will be 1. And are you seeing that or not in your output? This is Y, right? This is your Y. This is your output. And are you seeing this or not? See, the same Y, whatever the thing that was there in Y, that is being propagated to my output Y. That's it. Simple. Next. See, for example, let me place my cursor here at this instant. So for this, okay, so see here, what is the value of A here? A is 0. What about B? B is 1. B is 1. What about selection line? Selection line is 0. That's what we can see here. A is 0. B is 1. Selection is 0. So A is how much? A is 0. B is 1. Selection is 0. For this configuration, tell me what is the output. If selection is 0, what will be propagated to the output? Your input A. What is there in A? 0. So your output will be equal to how much? 0. Are you seeing the same or not here? Yes. Output is 0. See, my ABR 0, 1. My selection is 0. Then output is being propagated to the input is propagated to the output. Perfect. Okay. Is it clear here?
Okay. Sir, can you show the code? I want to take a screenshot.
Yeah, sure. No worries. I will share you the link, okay, in the chat box. Don't worry.
Okay. Sir,
Or
if I
if you
don't know the
want,
output of
I
the
can
characteristics, then how? Question from Sandeep Bangala.
come again. Oh,
If I don't know the output characteristics.
Mm, okay, that's where you have to use behavioral modeling style. Okay, it is not that you will know characteristic equation for everything. For example, 128 cross 1 marks. Have you ever seen any characteristic equation for that? It means that you have to solve 7 variable k map for that to end up having characteristic equation. Not possible. That is where the beauty of behavioral modeling starts. Okay.
In general, which style of modeling should we use? Question from.
Behavioral is the one that is used most practically.
Okay, sir, aren't we supposed to enter values for A and B and S mentioning bit format like one,
Okay.
0 and 2?
Okay, see, actually that you can do that, and there is nothing wrong even if you do this. Okay, however, it is, good programming practice to enter values like this, as I mean, it is little maturity to write like this. Okay, however, in your day-to-day life, if you keep on writing, you will be habituated. It's okay, you can even write like this here. Okay, as I have shown here in line number 12, nothing wrong even if you write like this or even if you write like this. Okay.
Okay, great, Prithvi. That's all we didn't. Sir, can you explain the test bench again? Question from Laya.
Test bench. Okay, yeah, sure. So see here in test bench, this is what we have already discussed yesterday actually. Okay, however, okay, I will discuss. See, whatever the inputs I have taken here, input and output, I simply declared them as input should be declared as rich and output should be declared as wire. That's it. And then in line number 6, I have done something known as module instantiation. Okay, I have done something known as module instantiation. This is where I called my DUT into my test bench. After that, I have taken one initial begin end block, and in this, what did I do? I have given some values. So this is my multiplexer, right? A, B, and S. So in order to verify its functionality, how can I do that? I have to give different values to my S, A, and B. So that's what I have done. I have given different values to S, A, and B. Okay.
Okay. There's a question, sir. Suggest a platform which will be used to simulate the FPGA and see the output.
FPGA, so you can use Vivado here. Xilinx Vivado you can use.
That's it, Prithvi. We don't have much questions today.
Okay, okay, great, fine. So let me place
Most
this
of them are
link,
clear. Yes, yes. You please.
let me place this link in your chat box
Then, yeah.
so that you all can, access it.
Mm,
Uh, Sorry, it seems I'm sending this message directly to someone. Uh, just a minute. Or you guys try, meanwhile, you please try to take a snippet of this. Okay, let me delete the unnecessary lines of code. Yeah, now it will fit. You can take this now. Here it is. It should be to everyone, right? Okay.
Srihari, tomorrow we're going to talk about protocol majorly. What is protocol and all?
Yeah, I have just pasted this. Yeah. You please go through that link. You will be able to see whatever the code I have written.
Yeah. Thank you,
Okay.
guys. I think we're almost done and we don't have much questions today. That's great. Hoping that you all understood the session well. That is reason we have less questions today. See you all tomorrow, the last day of the Silicon Symphony, majorly the masterclass last day. So we would love to see you tomorrow.
Yeah,
Thank, thank
don't
you.
miss tomorrow's session here. Tomorrow I'm going to give you few more insights on, like, how to get into the industry, and what are the different roles, even more roles on, like, where you could be placed, or what are your interests, and how you can be industry ready, or what are the things you have to do. If you join any coaching institute, that's fine, but even without joining with anyone, like, if at all you want to do something on your own, how to do, and what are the different platforms for it, what are the free websites which you can access for the course content. All those things, we'll be discussing tomorrow. So please don't miss tomorrow's session. Hope to see you all tomorrow again. Yeah. Thanks for your time.
Thank you,
See you
guys.
tomorrow.
Thank you. Any update regarding the batch and our groups will be shared on our channel as well as on Insta and LinkedIn handles. Our details are being posted in the chat box. You can surely contact us, follow us for the more details. And we do have a batch starting on Jan 20th of 2025. And we are expecting all you to join and take the course so that you'll get more information in detail. Thank you, Prithvi. Thank you, guys. Thank you so much. Have a good night.
Yeah. Thanks. Yeah. Thanks, everyone.
Thank you.
Good night.